Hello everyone, welcome to the second talk of the session. Now we have our next speaker, which is Aurelia Deshayes, who will talk about the contact process with inheritance sterility.
Okay, thank you. Thank you very much. So yeah, I'm from France, but currently I'm in Uruguay for 6 months. I'm very glad to be here again. I think my last visit was 10 years ago for River College also. So yeah, I really enjoy to come back to Santiago, and yeah, a lot of things changed in 10 years, but I'm still talking about contact process, so some things. Yeah, that doesn't change. So it is a joint work with Isabella Alvarenga, who just finished her PhD in Warwick under the direction of Daniel Valdesin. Yeah, so I used to start my talk about contact process with the famous sentence of Liggett, who say that it's a very famous process. But I think some of you already know that it is a famous, I will not defend it. And unusually, I will start with a biological motivation, which is a true one. It's not like, usually I give like false biological motivation, but this one, it's a true one. It's so the sterile insect technique. So the sterile insect technique, it's okay. It's a method to eradicate a population of insects, and so the technique is from the 50s, but it's still used today. And I found recent videos on YouTube about the use of the techniques in South America, and for example, in Chile, it's used to fight against the Mosca de la fruta. So the idea is to put a sterile mates in the population, which will reproduce, reproduce with females, but without offspring. So the idea is to decrease the population because they cannot reproduce, and to eradicate the population. But the problem with this technique is it needs high level of radiation, and those sterile mates have loss of sexual competitiveness, and they are more okay. So they compete with fertile ones. So the idea is to do like a partial sterilization. That is, so ask less radiation, and so we have a population of male who can reproduce and give a certain proportion of sterile offspring, another one of fertile ones. Okay, so it's not sterile anymore, but the child is with probability P is fertile, and with probability 1 minus P is sterile. Okay, so the idea is to add a spatial constraint and use the famous contact process model to modelize this model. So this modelization came from a discussion between Rinaldo Schinazi and Sonia Velasco, who is a former student of Hélène Saada. So the idea is to take an interacting particle system on DD, and each site has 3 states, -1, 0, 1. The 0 means empty, the 1 is fertile, and the -1 is sterile. And the dynamics are the following ones. So the 1 and -1, sterile and fertile, will disappear, dies at rate 1. And the fertile will reproduce, as we said before, That is, 0 will become a 1 at rate lambda. This is like burst rate, and multiplied by p by the number of fertile neighbors. And 0 become a -1 at rate 1 minus p lambda, a number of fertile. Yeah, is it the model clear? Okay. So for people that already know contact process is the same but without the -1. So the problem here is that the presence of site -1 creates like a random blocking environment. And so there is a lot of models about blocking environments. I will come back later about the model introduced by Daniel in 2008 with a -1, and then with Amitai. Okay, I will come back later on this model. This one is not attractive in the sense that if you start with a bigger configuration, it's not monotone in the initial configuration. Like if you start with more 1 at the beginning, you can have more 1, but also more -1, so more blocking. So it's not attractive. And Sonia Velasco proves that it's also not monotone in the parameters p and lambda. So if you increase p, you don't know what happened. It's not obvious. And if you increase lambda, neither. So yeah, the important thing is the not attractive, not monotone, and the fact that the environment is a -1 is depending on the process itself. It's not a random environment with an independent behavior of the process. Okay, so the first question about this kind of
question, monotonicity in which sense? Like,
okay,
-1 and 0. So
okay, so yeah,
is the -1 smaller than the 0, or they are?
Yeah, good question. Very, very, very good question. So for this talk, we will consider that 1 -1 0 1. But in fact, okay, in this paper, she also proved that if you consider that the sterile particles are between 0 and 1, it's not monotone either. And so monotone means that there exists a coupling when I can construct like two process with initial configuration or two process with different initial configuration or with different parameters, such that the stochastic order is preserved. So there exists a coupling.
Yes, and between time 0 and 1, or between the whole time?
All time.
Okay. So it's also not true that you are not monotone if you just check time 0 and time 1, but yeah, only those times, but without doing the middle one.
Yeah, I think. Okay, if you have time 0, it's always a problem. Maybe later, if you forgot time 0, we can have some monotonicity and attractiveness. But if you have the time 0 with the blocking, yeah. So the question is there a phase transition, that is a change of behavior of the global process when you change the parameter? And then after that, if you have a phase transition, you can ask what is the behavior of the process in every phase, and phase theorem. We will define that later. So the problem is because of the lack of monotonicity, it's not obvious to prove phase transition. So the idea of Sonia Velasco is to compare this model with two other models better understood. So I recall here the previous model. Here I defined the contact process. So 0 is empty, 1 is fertile. It's the same, but just there is no -1. Okay? So it's exactly the same. And the last one is called spont for spontaneous. So in the last one, you imagine that the -1 appear spontaneously, not as a child of a 1. So this one, the first two dynamics are the same as before, but to go from 0 to -1, it's appear at rate 2 1 minus p lambda, and it's not depending on the profile. The two, okay, it was a small error, it's a 2D, but I will work in dimension 1 later. Sorry, it's a 2D in DD. It's to be able to make a coupling with this process, and yes, you have the number of neighbors here. So we have the following stochastic order. That there exists a coupling, there exists a constriction of these three processes, such that your spawn is always smaller than your inherited sterility. I never said the word of the process. I realize inherited sterility is the name of the process that I am presenting. So IS, and which is always smaller than contract process. Very, very, very important. So if you have some doubts about, yeah.
Probably you said this, but when the offspring is not sterile,
Yeah.
it's offsprings in turn, they are standard, or they have also.
No, it's a fertile one. It's a 1.
It's a normal one.
Yeah, no, okay. 1 we care the inherited sterility. So when you will reproduce.
So all the offspring.
Yeah.
The descent line will be the same. Same type of.
Yeah. It's 0. Yeah. There is only 3 types: 0, empty, sterile, or fertile.
Es normal. Su hijo también puede ser. Digo.
Yeah.
No, pero.
Everyone has
Yeah.
offspring, and
Everyone is have the same probability of giving birth to fertile or sterile.
Everyone is normal. Or no.
Okay, so this stochastic comparison is very important. So this one has a lot of -1 because they appear spontaneously. This one has some -1, has a descendant of 1, and this one has no -1. Okay. So do you agree with this comparison? Do you trust?
The first one
We are far away from the application, no? Here is only the.
I will still it's about application. Later, I will be really far away when I will go to dimension 1. But until now, I'm still in the application.
No. Because you see, you have the insect, it's a nature. For them, you have p equal 1. And for the one you go to the laser, I don't know what, for those one, you have the p.
Yeah.
But here they have all the p.
Yeah, because I'm just.
So it's like, as I understand, you just consider the population coming from the laser. So that's why I said, well, is it population? Because you don't put them in the nature.
Okay, but you have to study first his behavior, and then we can try to make competition between the CP and the IS.
So I have one question. The 2 here is because you're in dimension 1?
Yeah.
Okay.
Yeah.
No,
It's a 2D in dimension D.
Yes, okay,
Yeah, but I will use it only in dimension 1.
Okay.
Later. My result is only in dimension 1, but for the moment, the definition are all valid in dimension D.
Yeah, no, but for the coupling, you need 2D. It's not true.
Yeah, it's 2D.
All right.
Okay, so so this comparison allowed Sonia Velasco to prove a phase transition. Because this bond process that we defined before has the properties that the IS does not have. Like, he's monotone in P and is attractive. So she could make a comparison with oriented percolation with quite a classical technique to prove that this process survives for a large enough P and lambda. And then, thanks to the comparison, she obtained a phase transition for the inherited sterility model in any dimension. That is, if lambda p is less than the lambda c, is the critical for the contact process.
Is it?
Yeah. Critical. No, more. Okay. Okay. So, but the idea is for lambda p small, the process disappears. There is no insect, radiated insect in the population. And for lambda larger than lambda c, there exists a p large enough, such that for the p larger, the IS survives. So it survives with positive probability. It's never probability 1 with this kind of process. It's always survive with probability and with a positive probability. So when I say there is survival, sometimes I always with positive probability. But
You're starting from one side.
yeah, for finite, for finite. So in this simulation, it's one. Yeah.
So in this picture, what are the different colors?
Yeah. So here you have the 3 coupled process. So the construction is the one that give you the coupling. So the white have the sides that are one for everyone. That is SPONT, IS, and CP. The gray is one for IS and CP, but not SPONT. And the gray, left gray, is the one for CP, but not IS and not SPONT. Okay, so you see that SPONT is the smaller, IS in the middle, CP is the bigger. Okay, so there is a lot of there is still a lot of interesting question about the phase transition. I will come back at the end of the talk. Yeah.
Sorry, in your picture, time is upwards?
Yeah. In the community of contact process, we always time upward, but yeah. Okay, so there are still a lot of questions about the phase transition. For example, I will come back later about the open question. And now, looking at this picture, so it's known that the contact process has a linear behavior, and we want to prove that it is the same for the 2 other processes. So, that is our result.
I have a question from the last.
Yeah.
Is there like a good estimate of this P, or is it like just P super close to 1, whatever is needed?
No. Yeah. P really close to 1 for the oriented population comparison.
Okay.
Maybe we can find an estimation but no, on her result it will be a bad one.
Okay.
But we don't know whether they're like for P bigger than this P hat, it's true.
Yeah.
Yeah, what?
But we don't know. Yeah, okay, it's true for every P bigger than P hat, but we don't know what is P hat. P hat is really close to 1.
Okay.
Yeah, but
we know that.
but there may be some points that in the middle that they work. So
No.
it could be.
No, because SPONT is monotonic.
Oh, yes.
So when it survives for 1 P, it survives for probability for every.
Yeah, but I mean for IS.
But IS is always above SPONT.
Yeah, so you have an interval that I agree, but then could you have some points before the interval for IS?
We don't know. Before the that's the open question about the phase transition. We think that the phase transition for IS is bigger, and maybe there can be some point, but it's conjecture. There is another phase transition. The P hat for IS is smaller, but it's also there is kind of a hidden monotonicity.
What about the initial conditions?
Okay, so the initial condition. So here we always take 1 point. You can take a finite amount of 1. And if you take an infinite amount of 1, it will never disappear and other behavior appear. Okay, you can ask a lot of questions. But just take 1.
And no minus
1. Yeah, you can take anything.
Really?
Yeah.
But because -1 kind of block everything, right?
Yeah, but they will disappear at some point. Really quickly, in fact.
For the you stated it for I8S, but it's true for SPONT as well.
Yeah.
The second version.
Okay. So it is true for SPONT. That is the proof. It's an easier proof for SPONT. But here we are interested in IS because it's harder for IS
Okay,
because of the lack of monotonicity and attractivity. That's why I just write it for IS, but it's for IS and SPONT.
Okay.
Okay. So, our result with Isabella is to prove the for P and lambda large enough, as before, but like large enough, that we have a linear speed and Gaussian fluctuation of the position of the rightmost one. I say rightmost. If you start with only one, you can say leftmost, but rightmost allows you to start with anything else here. Okay, so the key element of proof is to like find renewal times that like cut the evolution in ID parts in order to use the law of large numbers, CLT, and classical tools. So okay, so now. So this is the result, and now I want to explain our idea, some idea of the proof. And for that, I will come back to the classical contract process. So when Harris introduced the classical contract process in 1974, he introduced the graphical construction of the contract process. So time is going up, space is the horizontal line. Here is okay. I forgot to say that our result is only in dimension 1. Yes, it's disappointing. It's mathematical and not biological now. So the construction is in each site. You put a Poisson process of rate 1, which indicates the potential death or recovery. Okay, so all vocabulary, sorry. And in each edges, you put an arrow which represents the potential infection. And you start, for example, with the site 0 in state 1. And you follow the graphical drawing. And if there is an error, you can go through the error. And you stop when there is a cross. Okay, so so there is an infection path, or an infection path from XS to YT if there is a path in this space-time diagram. Okay, and if X is infected at some time and there is this infection path, then Y is infected at times. So for people who know contact process, it is okay. So obvious thing, but it's really important that you just need to know that there is a path from X to Y. You don't, you ignore everything else in around you. And if you know that at some point this is infected and there is a path, then the other one is infected. And in our process, SPONT and IS, it will not be so easy because maybe in the way you have a path in this drawing, but there is a -1 blocking. So you need to know more about the environment, and just the percolation structure here is not enough to prove. Okay. Okay, so forget about that. It's just the phase transition contact process, too many lines here. I want to go back to the two very important properties, that is attractivity, which means that there exists a coupling such that so here is for contact process, that is only 0 and 1. If B has more 1 than A, then it will be the same for all time. Here we have like minus 0, 1, and it will be if A is less than B in each point, then eta of A is less than, okay? Point by point at each, yeah? And another very important for the contact process that, so for a long time, I was convinced that only attractivity was interesting and additivity was just a plus. But in fact, additivity is important. Like, for example, SPONT is attractive, but not additive, and it will have some impact. So it's so additivity is this one, is if you start with A union B, so we with that A maximum. Yeah, maximum. Yeah, okay. Okay, then it's the same. Okay, just define an operator between the 0, 1, and 1. So the additivity is stronger than the attractivity. Okay, so for the contact process, the results are quite old. First, Durrett and Griffith prove like a coupling with orange percolation, and prove this result. It will be useful later, that the extinction time of the process have exponential tail, and for example, 84, Durrett proves that the rightmost infected particle have a linear behavior, and the key element of the proof is almost subadditive ergodic theorem. So I want to something. Okay. So here's for the contact process, for example, so space, time, and we start with only one particle, and you have like this infection path. We suppose that we are in the supercritical phase, and we suppose that we have survival, so there is like an infinite infection path, okay? And you want to study the RT, the rightmost one at time t. Okay. The idea is that if you look at S at the rightmost one at time S plus t, you can go first at the rightmost point at time S. Okay. And then go from the configuration at time S and look at the rightmost at time t, but starting from the configuration at time S. Okay? But thanks to the attractivity, you say that if I start with this configuration at time S, if I forgot everything and I just keep this one, it will be less than RS plus something that has the same distribution than RT. Okay? And this is the subadditive.
This is like the displaced version of the configuration, like you move it to 0.
Yeah.
Okay.
Yeah. So to have this so subadditive inequality, subadditive property, you use attractiveness. And this proves that there exists an alpha such that St over T converges to alpha. And to prove that this alpha is positive, you need more than attractivity, you need additivity. Oops.
Excuse me.
Yeah.
I misunderstood something because for me, because you start with more than one particle as a file. Larger, so it should be larger.
Yes.
But it's
Yeah.
I agree with
Yeah.
Like to minus.
You're right. But it's working. Both of you assume.
No.
Okay, so and then some years later, from one part Galvez and Franciti and another part Cruikshank prove a central limit theorem. And I will
It works. It works only if
it's the in distribution. It's not. This is something that has the same distributions and.
Yes, but it actually doesn't work if there is extension.
Okay. Here, okay, yeah, I told, but it's conditioned to survival.
Yes, but the thing is that when you're taking the rightmost one, it's not supposed to survive.
No.
So the inequality is neither superior neither inferior. There is no. It seems to me that no, there is no inequality because there is no, no conditioning on the stuff.
Yeah. So it was really like.
Yes, everyone.
The idea, but
Okay.
everything is conditioned to survival, and the distribution is okay. So inequality is in distribution. You're just looking at some random variables that RT conditioning to survival, and this one is always finite. But if you this one will extinct in the drawing, but the distribution of RT conditional to survival is always finite.
Okay.
So, but okay, it was just to give an idea. No, it's a very, very big question. Okay, so I just will give you an idea of the central limit theorem. Okay, so the idea of Cruikshank is we have the same picture. And so this point is the rightmost and has infinite descendants. And these points are like excursions that we don't care about. And this point is the next rightmost with infinite descendants. Okay? And so, yeah, something here is weird, but when we are here, and this one has infinite descendants, you recover the behavior close to this one. If you forgot about what is happening here, this one and this one behave in the same way, always conditioning to survival. So these points are kind of renewal times, and you can have like law of large number and some limit theorem to say that these points are so this evolution is linear, and the rightmost is never too far from this one blue rightmost. But for this proof, you really need the attractivity and the additivity, because you need to forget everything here. If there is 1 and -4, I don't care. And even here, if there is, so you know that there is no 1 because it is the rightmost, then it's Pons or IS, it could be 0 or -1 that change the game. So, for example, the environment here is not the same that environment here. So the lack of additivity or attractivity make this method not working. Okay, so this is the behavior of the really nice contact process. Okay, so just in time. So small parentheses. So there are a lot of variation of contact process. It's a very robust model. So I will give some of the extension. For example, Duret and Skenazy in 25 years ago, but it's still there is still an open question, and Angel and Rolla are working on it. Introduce a contact process with modified boundaries. So modified boundaries is when you are the rightmost, you have a rate different than when you are not the rightmost, for example. And the small change make appear a lot of problems. For example, contact process in dynamic random environment. So there is 2 papers from 2008 from Stife and Rafheimer and Reminick. So they are not exactly the same model, but they have something in common. And one from Amitai and Daniel, which is so, for example, in the paper and in this one, so you put the dynamical edges. We are sometimes here and sometimes not here, and you can use these edges when the edge is present. Okay. During my PhD, I introduced like the contact process with aging, which was like when a particle appear, it appear in at rate 1, like is sterile for long time, like you are a kid, you cannot give birth, and then you have another exponential time to wait aging to be able to give birth. It was attractive and it was a nice one. Okay, or other this is contact process with steering, where the particle can switch place sometimes. And at some point during my PhD, I was very I don't know, naive, confident, and I want to put like a shape theorem for all these processes. So I tried, I failed. 10 years later, there is a paper. Okay, it exists, but it asks a lot in the process. It has to be additive, and in fact, almost all these processes are not additive. Just this one, the contact process, and the one from my thesis. So it's a very weak result, because it asks a lot to. So it's not so easy to make a general theorem about linearity and shape theorem for this kind of process. That's the conclusion. And there is a recent paper. A recent paper from Saylor and Reitmeier. I didn't read it yet, so I cannot talk about it, but I think it solves some problem about this question. So, coming back to our inherited sterility process. we cannot use this kind of I will look for the rightmost with infinite descendants because it's not renewable time because we cannot ignore the information that we have. So we have to find another good property. The good property is I am the rightmost and I have infinite descendants. So the good property will be really, really strong. At the first view is the rightmost position is unchanged until time under any modification of the configuration. So the thing that I'm saying is I'm looking at this point. If I change, so I keep this one being 1, and if I change anything here to be -1 or 0, and anything here to be 1, 0, or -1, the rightmost here is the same. So the first idea, it should never happen. It's too strong, but no. And so okay, this good property will have the good behavior to be if it's true until t, and if it's true from t to infinity, it will be true to infinity. Okay, and we will introduce this time f, which is the first time where this property is not satisfied. Okay. So the property is true at time 0. Okay, because it asks for the configuration to have the same rightmost. Okay, and the result is that it is possible that this property is always true. But the probability that f this time is infinite, this property is always satisfied, is positive. And we have exponential decay. That okay, if this time, if I wait too long, it will be finite quickly. Okay, if it's true during a long time, it will be true infinitely. Okay, so why?
Sorry, I don't understand the good event. So what do you mean by any modification of initial configuration?
So here you have a 1.
Yes.
I can change anything here, but -1 and 0 only, and anything here.
Yes, okay.
Any change. I just keep
as long
the
as
same rightmost at the beginning.
I know this is for both spawn and IS?
Yeah.
Okay.
So P is a proposition applying to a given configuration and
No. Okay. Yeah, I will. So
It's an event.
the configuration is the initial configuration.
Mhm.
But in fact, if it's true for any change of configuration, it doesn't count of the configuration. If it's true, this doesn't count. But if it's not true, this counts.
But you still need to leave like the one particle at the beginning. You cannot change that.
Yeah, the configuration is the initial one. I start with an initial configuration C, which is blue. Okay, I take a time T red. I change anything. The rightmost is still the same than the one from my red one.
For the usual copy.
Yeah.
Yeah. Okay. And okay, so it's for given. It only depends on the type.
Yeah. Okay, but if it's always true, it's only depending on the time. But if it's wrong, it can depend on the initial configuration. If it's true, you can have any modification. So this one doesn't count. You choose. But if it's wrong, if the property is not satisfied, maybe with another initial. Okay, no, it does. Okay, we need the configuration, but it does not depend on the configuration, just on the position of the rightmost, if you want.
The freedom with this configuration is just about the -1s and the zeros, right? You cannot place any additional ones.
See, yes.
At At the right, to the left.
at the yeah.
Okay.
To the left, you can put one.
Okay.
To the right, you can. The only thing that I ask is just say the same first rightmost.
Okay, but what is the arrow? Well, the arrow T arrow infinity.
If the property is true until t, and imagine, okay, define like that. If the property is true between time t and between time infinity.
Okay. Oh, it's not at a given time. It's up to a given
Yeah.
time.
Yeah, until time, not up,
Okay.
until this time.
Okay.
So I'm confused. So this is something to prove, no? It's not completely. It's not omega by omega, no?
This one
Yes.
is omega by omega.
So then I'm lost because for you say you don't change the rightmost one.
Yeah.
Okay. Okay. So this is the trick.
Yeah.
So if
Yeah.
you don't change the rightmost.
Yeah. Okay, so the idea is to understand when, if you take two different configurations, when they will split, when the rightmost will split. What can happen to make fail the property? And it's not so easy it's easy for the contact process, not so easy for spontaneous. But the idea is, in fact, this long sentence, that the first moment where the rightmost between, for example, a configuration, starting from a configuration C and starting from the worst configuration will be 1 and -1 everywhere. Okay? If you are looking, when the configuration will split at the rightmost, it has to be when the rightmost try to jump to the right to a site that has never seen a healing marks. Okay? The idea is if when I try to jump to the right, there was a healing mark, in fact, the environment is the same and they will both jump. Okay? And in fact, it's the same for IS. The difference is there is no worse configuration for IS because it's not attractive. So this one, I cannot say that it is the worst configuration. Okay, so I have to work in more general and to take two configurations, C1 and C2, with the same rightmost at the beginning, and then try to study more carefully when the rightmost can split. Okay, so the idea is now I know that to split the rightmost, it's when I try to jump to a site that has never seen a healing mark. And when the time goes up, it's really the probability that the site has not seen a healing mark became really small, because the idea that the environment mixed over time. And this is the idea of this picture. So here you have, you know that SPONT and IS are smaller than contact process. But contact process is linear. So in fact, SPONT and IS are constrained to this zone with high probability. And then you can make the green zone the zone where sites have not seen a healing mark. And at some point, this zone will be disjunct, really disjunct with high probability. So in fact, every time a site will try to jump to its right, it will be somewhere where the environment is the same for both processes, and so the rightmost will stay the same. So that's the idea of this. If if the process stays here, the healing mark stays here, I have like some initial event, and I know that there is survival, then my property will be infinite. That the rightmost always coincide when I change the configuration. And for the exponential tail, the same idea. It's more complicated even, but it's the same idea. using the fact that we also know that the extension time for contact process have extension tail. Okay, so now it's over. So you have this property that have positive probability and exponential decaying tail. And so you will look for the first time that the property is true, and then you will wait a little bit and then look for the next one, and You have the good property that is this first time happens really quickly, and when you know that this first time is 0, for example, the next one happens also quickly. So at the end, you have like an ID structure for this time and this rightmost position, and all the job is done. You can just apply the law of large number and central limit theorem, and to say that you have rightmost speed, linear speed of the rightmost, and Gaussian fluctuation. Okay. Okay, so just I will end with some open question. So so this proof, okay, is only true for lambda bigger than lambda c and p bigger than p hat, because I need the behavior of the spawn process that is known to the computation, but in fact, here you see that the IS can survive without the spawn, and obviously we want to prove that there is linearity even the spawn dies. And here you see that you have like really 3 different velocities. That is an open question. Is there? Can we prove that there are strict monotonicity of the velocity? Obviously, in dimension bigger than 1, there is a like kind of shape theorem, and yeah, a lot of question about the phase transition. Yeah, okay. So I will stop here. Thank you. The picture of my collaborator. So here is Isabella for this project, my PhD advisor, Regine, and Marco, is Marco Saylor. So yeah, a lot of Sonia Velasco, a lot of names that appear in this picture.
Yeah. Questions?
Yeah.
Do you know anything about the proportions of each state in the long run?
Okay, so which model?
Which model?
Yeah.
Oh,
Okay.
yours.
So, no.
Yeah, yes, that one.
No, mine, no. For the contact, but okay, so there is a lot of results about the contact process, and for each PhD student, you can ask, can you generalize this result for the IS, for example? But for the contact process, so we know that there is an invariant measure. We know that we can put Bernoulli under this invariant measure. And we know that at long time, you see inside this cone the invariant measure, for example. And the problem is for IS, it is not attractive. So it's not, you don't know if you have an invariant measure. It's a good question. I think that in fact, IS have some attractivity hidden, and I think there is an invariant measure, and I think you can have like some kind of similar result, but the answer is no. There is no result.
Or maybe you have a guess for higher dimension, because in that case you can write a heuristic, mean field limit or something, and you can write some ODEs for it.
Yeah, it's true. Yeah, you can. I don't do this kind of stuff, but yeah.
So what happens if instead of being infertile, they are just less fertile? Can you still do some kind of
Okay.
idea?
So okay. So if you have less fertile but still bigger than lambda c, it's like a nice random environment. Easier, it is done. If you have less fertile, like less than lambda c, it's a real. Okay, no. Okay. No, it's kind of okay. Yes and no. It's still like okay. It's kind of a dynamical environment, but with like a small parameter, and I think it will be the same kind of question. But here, if you say I'm less fertile, you can say that IS less fertile. Okay, is bigger than IS, no? Because if you give to -1 little possibility to give birth, it will be better than this one, and I think you can do exactly the same.
I was wondering if there is a spectral approach to that or not. So first, you will take a box.
Yeah.
A structure box that is too large. And it will be a process which is absorbed. So now, when it is absorbed, naturally, you have the rate of absorption, the first direct value. And you have also the quasi-stationary distribution. So can you deduce something about them? Say something about your process. So in particular, in this case, you can start in the middle, you have a box. The rightmost, does it correspond to something?
Okay.
In a spectral view of the...
Yeah, okay. Depend of your supercritical regime.
So here, on a finite.
Yeah, okay.
Finite box. So I condition not to be disappeared.
If you take a finite box, but you are in the supercritical regime, the contact process is.
Yeah, so first question, you're right. What corresponds? How can I see if I am a super on a finite box?
Yeah. So it will disappear.
Huh?
It will disappear at some point,
yeah,
but it will be really long. Because the contact process is like a metastability behavior that it takes an exponential time to disappear, and during this long time, you think that it is an invariant measure, but in fact it is not, and it will at some point disappear.
Yeah, but you have the quasi-stationary.
You are the quasi. Wait.
That's why I didn't talk about the and when we have some processes which are absorbed, furthermore, they can have a family of states, of quasi-stationary states, not the whole one, but the one associated to the other eigenvalues.
Yeah.
So I was wondering, this increasing linear, surely there is an spectral interpretation, but I've never seen, because from what I have seen, people working on statistical physical model, when you say, what is a spectral, what is the eigenvector associated to that?
I didn't get to do that. I was very proud of myself, but yeah.
Yeah. So I speak to what is the girl in Lisbon? I forget her name. But I see that people, they have two communities with on Markov processing.
Yeah, I agree.
But they don't talk so much.
Yeah, I agree.
Yeah, there is Nandi, but so after that, I was thinking of your mosquitoes. The one in my room, they don't stay at the same place. So
yeah, sure. Yeah. So good.
And otherwise, I will be able to kill them very easily.
Yeah.
So is there a model where you have a motion? Because furthermore, each site. Why there is only one strength. So I would like to then evolve and to split at some point, this branching like you are doing. While doing the branching, can you say there's something with that? Will it be linear? Yeah,
it's a very interesting question, but you need to understand first the simpler model.
Ouais, je sais pas que ça.
So, but
Anyone else? Some question?
I have a question. So, so we asked for the supercritical case and a final false, but maybe for a subcritical case, have USD study?
okay, so for control process, yes. Like me and Leo. So for the contact process, we know that there is a quasi-stationary distribution, and we know the behavior of the process because, like, there is like exponential distance between the points that survive, and I think the method is quite robust, and I think you can do the same for this process. And then you can study, to come back to the question of Laurent at the beginning of the talk, maybe the competition between a contact process and the inherited sterility one, thanks to this kind of stuff.
Any further question? Well, if not, let's thank Aurelia again.